All right, welcome to The Explainer. You know, sometimes in chemistry, a single graph can tell you a whole story. Today, we're going to crack open a classic exam question and see just how much information we can pull from one simple curve. All right, let's get right into it. Think of us as chemical detectives for a minute. We've got a bit of a mystery on our hands, and this titration curve, well, that's our main piece of evidence. And believe it or not, it has all the clues we need to solve the whole thing. So every good investigation starts with the case file, right? Here's what we've got. One unknown reaction, a lineup of 3 possible chemical suspects, and of course our star witness, the graph.
So here it is, our central clue. What you're looking at is a plot of pH versus the amount of some chemical, called a titrant, that we're slowly adding. The shape of this curve, where it starts, how steep that drop is, where it levels off, that's where all the secrets are hiding.
And here they are, our lineup of suspects. It's got to be one of these 3 chemical systems that produce the graph we're looking at. Our job? Figure out which one's the culprit. Okay, time to analyze the evidence. We're going to break this graph down piece by piece and build a profile of our mystery reaction. Let's figure out what story this curve is telling us. First things first, let's look at the starting line. See over there on the left? The pH kicks off at around 11. Now that's basic for sure, but it's not, screamingly basic like a pH of 13 or 14 would be. That's a huge clue right there. It tells us we're almost certainly starting with a weak base in our beaker, not a strong one. All right, clue number 2. Check out that super steep vertical drop in the middle. The very center of that nosedive, that's what we call the equivalence point. Now, if you follow that point straight across to the pH axis, what do you see? It hits somewhere around a pH of 5. That is well into the acidic range, way below neutral 7. Okay, so let's put our clues together. We started with a weak base, right? And our equivalence point is acidic. Those 2 facts combined, well, they paint a very clear picture. This can only happen when you're titrating a weak base with a strong acid. That's our profile. Now that we have a solid profile, we can head back to our suspect lineup. It's time to see who fits the description and who we can cross off the list. Let's check out suspect number 2, hydrofluoric acid being titrated with magnesium hydroxide. This one starts with an acid in the beaker. That means its graph would have to start at a low pH and curve upwards. Our graph does the exact opposite. It's a total mismatch. So, nope, system I is out. Okay, how about suspect number 3, carbonate with nitric acid? Now, carbonate is a little tricky. It's what we call a diprotic base. Basically, it reacts in 2 distinct stages, and what that means for a graph is that you'd see 2 of those steep drops, not just 1. Our evidence only has 1 drop, so that's another mismatch. System 3, you're out. Well, look at that. By process of elimination, there's only 1 suspect left standing. System I, ammonia, which is a weak base being titrated by hydrochloric acid, a strong acid. Does it fit our profile? Weak base start, check. Strong acid titrant, check. It's a perfect match. I'd say, case closed. But wait, there's more. Just because we've identified the reaction doesn't mean the graph is done talking to us. We can actually pull some real numbers out of this thing. Let's start by figuring out the exact concentration of that ammonia we started with. So how do we do that? We can actually work backwards from that starting pH of about 11. From the pH, we can figure out the pOH, and from that, the concentration of hydroxide ions. Once we have that, we just plug it into the equilibrium expression for ammonia, do a little bit of math, and that'll spit out the initial concentration for us. And when you run those numbers, you get this. The concentration of the ammonia in the beaker at the very beginning was about 0.056 molar. Pretty cool, huh? Okay, so that's the base. But what about the acid we were adding? Can we figure out its concentration? You bet. For that, we need to go back to our equivalence point. And looking at the x-axis, we can see that we hit that point right after adding 25 milliliters of the acid. Now here's the magic of the equivalence point. It's the exact moment when the moles of acid you've added are equal to the moles of base you started with. This leads to one of a chemist's handiest little equations, M1V1 equals M2V2. From here, it's pretty much just plug and play. We're looking for the acid's molarity, and we know we used 25 milliliters of it. On the other side of the equation, we have the base's concentration, which we just found, 0.056 molar times its starting volume of 20 milliliters. You do a tiny bit of algebra to solve for that missing M, and there it is. The concentration of the hydrochloric acid we were adding was about 0.045 molar.
I mean, think about that. We figured out the identities and the concentrations of both chemicals, all from just looking at this one curve.
Okay, for one last thing, let's play a little what if. What if we flipped the script? What would the graph look like if we started with the strong acid in the beaker and dripped in the weak base?
Well, the whole story would basically flip upside down. You'd start way down at a very low pH because of the strong acid, and the curve would sweep up as you add the base. But here's the interesting part. The equivalence point would still be in the acidic range. Why? Because the final product, the salt that's formed, is itself acidic.
And really, that's the whole point of this. Every single point on a graph like this, every curve, every steep drop, it's all part of a larger chemical story. It just makes you wonder, doesn't it? What other chemical secrets are just hiding in plain sight? Right there in a simple graph.